Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So welcome back. So can you guys hear me?
Yes, Doctor.
Okay, thank you. All right, so let's continue. So this is discrete time Fourier transform properties chapter, part 2. Okay, so we have seen part 1. So how we use the properties. So especially the symmetrical properties of the signal, so that we can use the symmetry properties, so that we can have a simplified equation. So other than using the original, so then you have an option either to use the original equation, or you use a simplified equation. Okay, and then we have seen also this table, so which is some of the properties. So we have a linearity, time shifting, convolution, those properties. And so far we have seen one example, which is on the symmetrical only. So we haven't seen example on these properties. Okay, so that will be on our second example. And our second example is what we call a delayed symmetry FIR. So it is a symmetry, but it is delayed. Okay, so for example, so this is the example 1 1 1. This is symmetry. But if you want to have an even and odd symmetrical, so actually this is symmetry. This is symmetry, but not even or odd. Okay, because the symmetrical line is not at n equals to 0. If you plot, this is like 0, 1, 2. So is this a symmetry? Yes, it is a symmetry. But this is not evenly symmetry. And of course, this is not oddly symmetry also, because the symmetrical line is actually here. So this is the symmetrical line is at n equals to 1. So if you want it to be even or odd, the symmetrical line is supposed to be at 0. All right? So, but it is a still symmetry. So this is what we call a delayed symmetry. Because originally it's supposed to be, if it is even, so this is even. This to this, so we have delayed the signal. Okay, so how much? By one sample. So if you have even signal, this one, so this is actually a delayed version of this one. A delayed sample by one. Okay, a delayed signal by one sample. So then yes, we can still use the property of a symmetrical. But because it is a delayed, so we need to use another properties. So which is, so this is the one that we have. The time shifting properties. So if we have a delayed, so this is a delayed. If we have a delayed signal, so actually the DTFT is just whatever you have on your even or odd signal. This one, the symmetry, the original, multiplied by E minus J omega ND. Okay, so then you doesn't have to solve everything from scratch. So you just use a simplified formula for symmetry signal, and then just multiply it by E minus J omega ND. So how many, what is the ND? So it is actually how many samples the signal is being delayed. Okay, so let's go to that example. Okay, now again, we will try to find what is the impulse response, what is the frequency response, the magnitude response, the phase response, and the magnitude response in dB. Okay, for this signal. This is a 1 1 1. So what is our previous example? Example 1. So this is a 2 and then 0, 0, 0, 2. Okay, so now we will do a 1, 1, 1. So if we let a symmetry impulse response HEN, so let's say we have a HEN, the symmetry signal, the even signal. So this is the even signal of this version. Okay, so if we let this signal just partially, we are assuming that because we want to use this symmetry formula because it is easier. Okay, because it is easier because we just need to multiply to cos. It doesn't have to use the E minus J omega n for this one. So HEN, so for this, if we shift it so that we can have this one. So that's the n equals to 0 is at the center of that impulse response. Okay, then this is a 1, 1, 1. Then actually our HN here, this is HN. So it is just actually HE of n minus 1. Okay, so this one actually is just a delayed version of this one by one sample. So this is how we describe it. So then we can solve this one and then use a time shifting properties to solve this one. Okay, solve this one first and then use the shifting properties to solve this one. Okay, let's do that. So this is, so now what we have is actually something is missing here. So this one's supposed to be E minus J omega ND. Okay, what is our ND? And ND is 1 here. So if the ND is 1, then we can simplify that. E to the power of minus J omega multiply by the frequency response of our even signal. So this is the even signal. So you solve this and then multiply with E minus J omega. So why E minus J omega? Because our ND is 1. Okay, so this is actually omega multiplied by 1. So E to the power of minus J omega. So then we can solve this because we have this. This is E J omega. Something is missing here. So this is from the formula of this from this table. Because if our signal is even, okay, even means evenly symmetrical, so we can use this equation. But if it is odd, we can use this equation. So now we are using this equation. So we need what is the value at n equals to 0, and then the rest need to be multiplied by cos omega n. So then we have x0. So what is x0? X0 is 1. So this is where we have 1 here. And then you need to plus with 2 multiplied by this n is actually start with 1 up to infinity. But at the positive side, so we have only 1. So this is actually when n equals to 1. So, so this is where x0 plus 2x1, because we just have x1, cos omega. So because the n is actually equals to 1. This is when n equals to 1. So the n equals to 1, so this one becomes omega only. All right, so and then we just solve this one. So this is E minus J omega 1. This is 1 plus 2 cos omega, because x1 is also 1. X1 is also 1, so this one becomes 1. 1 multiplied by 2 and then multiplied by cos omega. So this is the one that we have. So it is h omega is actually equals to E to the power of minus J omega 1 plus 2 cos omega. So that's the frequency response. And we can do some manipulation on the maths so that we can get our magnitude. Because if we look at this one, so when we have a delayed signal, delayed symmetry signal, our frequency response is not entirely real value. Because now we have this E minus J omega. So actually we have the imaginary value here. Okay, but this kind of imaginary values, actually we can handle this easy. So rather than expand it, we can expand this. We can expand this into a cos and then minus j sine omega. We doesn't have to do that because we can manipulate it better using some tricks. Okay, let's write that again. So what is our h omega? Our h omega is e minus j omega 1 plus 2 cos omega. Okay, now let's assume that this one. Let's assume that this one is equals to alpha, because now we want to manipulate this thing because we want to solve this easily, right? So we doesn't want to expand it. We doesn't want to expand this to cos and sine. All right, so let's say 1 plus 2 cos omega is alpha here, alpha. So actually this is h omega. We can say that it is actually equals to alpha multiplied by e minus j omega. If we expand, we get this one, but we doesn't want to solve this thing. So we want to solve this one straight. Okay? This one, we doesn't want to use this. We want to use this one. So what is the magnitude response? The magnitude response is actually this one. This is the magnitude, so which is the absolute value of h omega. But we have another one, which is this is actually previously we know that this is actually energy. Energy, or sometimes we just simply call it a magnitude square. Okay. So of course we can get a magnitude from magnitude square. This one is just you take a square root of this a magnitude square, then you will get this one easily. So but why we need to do this? Because we want to solve this one easily. Okay, we doesn't want to solve this one. This is a bit complicated to solve. So for the magnitude square, so what we already know is actually if you go back to our previous notes, so actually magnitude square is the original magnitude response, the frequency response, h omega. You should multiply with the conjugate. The magnitude square is actually the original frequency response is multiplied by the conjugate of that frequency response. So then, so what does this mean? Because what is a conjugate? Conjugate is actually the sign of the imaginary part is changed. It has an opposite sign. So we have this alpha e minus j omega. So this is alpha e minus j omega. And then this is the conjugate, because this is a negative. Then you will have this one as a positive. Okay. So do that, multiply e minus j omega multiplied by e j omega. So actually this is this one becomes alpha, of course, a square, and this is becomes e minus j omega plus j omega. Okay, when you do that, it becomes plus. So negative plus positive, you will get e to the power of 0. Alpha squared e to the power of 0, which is equals to alpha squared multiplied by 1. See, it gets easier. So now we already cancel out the imaginary parts. So we have alpha squared. And alpha squared, this is actually a magnitude square. You want to have a magnitude. So you just do a square root of it. So whatever values you do square, you will have a positive value. So that's why when you do a square root, you will still get a positive value. So actually it's just whatever it is, this is the magnitude. The magnitude is just that 1 plus 2 cos omega. This is actually from the symmetrical signal, the evenly symmetrical signal. So this is the one. So we can just remove this imaginary value easily. Okay, because of this, because we just have this thing in front. Because the alpha is real value. The only thing which is the imaginary value is this part. So we can easily remove that. So So that's why the magnitude is actually just a 1 plus 2 cos omega. So it doesn't have to solve this one. It doesn't have to expand it to solve it. So, and the phase response is actually equals to tangent inverse of the minus alpha. This one, actually this is a minus alpha. Sine omega and then divide by alpha cos omega, which is, we do this tangent inverse of tangent omega. Right, so what we can conclude here, and then we get a minus omega. So actually this is from this one. So if you have a minus omega here, so you will get a minus omega here. If you have a minus 2 omega here, so you will get a minus 2 omega here. So this is where, this is another interesting thing, if we have a symmetrical signal. Because the magnitude become a simple, the phase also becomes simple and fixed to some values. Okay, so what is actually the phase? The phase is just what, how many delays that we have. So now the delay is actually represented by this one. It's a minus j omega. Okay. So let's say we have another example. 0, 1, 2, 3. Let's say we have another one. 4. Let's say this is a 2, 1, and then 1, 1, and then 2. Right? So let's say this is our Hn. Straightforward, you can say that the phase is actually equals to minus 2 omega. Okay? You doesn't have to do any calculation. Because how do we know this? Because this is actually, this is a delayed version of, we can have minus 2, minus 1, 0, 1, 2, which is, this is 2, this is 1, this is 1, this is 1, and then this is 2. So actually this is just a delayed version of this evenly symmetrical signal. So how many we delete? So we delay a delayed version of that one. So it is the delay. The delay is n equals to nd equals to 2. Okay, because you push this one, push it to the right by 2 samples. Then the phase is straightforward, equals to minus 2 omega. So because if you get this is let's say this is our Hn is actually equals to He n minus 2. So this is what we have. And H omega is actually just equals to E minus J2 omega of the He omega. Okay, so that's why the phase is simply as a minus 2 omega. And then what is the magnitude? The magnitude is actually equals to the magnitude of He omega. This one. So we just need to solve that. All right, so this is actually just a proof. Then you can do that kind of a simplification. So that's why this symmetrical signal is very interesting. We want to have everything to become simple and easy. Okay, and we will do more analysis later on why actually this symmetrical signal for FIR is actually very good. It actually is very good. So there's another thing which is it is actually good. Okay, so we have seen now one, if it is symmetrical, when we do a realization, so it can reduce number of a process, it can reduce number of a memory. And when we do DTFT, so now we know that the formulation is quite simple. Okay, the phase can be found very simple. Even the magnitude can be found you can find the magnitudes quite simple. Okay, so, and of course, this is the magnitude dB. You just need to multiply by 20 log 10. So I cannot just sketch this one. So we need to use like a MATLAB to display it. So, I didn't plot it. Okay, so any questions so far? Okay, because most of it we are focusing on a symmetrical signal. So this is where the properties becomes very handy. And again, I'm just saying it again. So what we do here is all of the example is for FIR, finite impulse response example, because the symmetricity doesn't really work on IIR. So normally IIR, the Hn, the impulse response of a IIR, so it doesn't get, it's very difficult to get a symmetrical shape. Okay, so on the FIR, we can control it. We can really control it on how to get a symmetric signal. We will see that on how we design FIR later. So, and we did that design. So we designed it so that we can get a symmetrical Hn. Okay, so if there is no question, so let's continue. I'm going to skip example 3. Let's go to example 4. And now we're going to discuss a bit on convolution properties, because what is a convolution? Convolution is actually a solution to our LTI system. So you have an input, you have the filter, okay? So how to get output? Do convolution, okay? You can do convolution. And it is actually quite unique. The convolution is only done on FIR. So if you have a IIR, so actually you cannot implement that. You cannot implement convolution on IIR because a convolution needs a finite number, okay, to do that. So if you have a IIR, infinite impulse response, so you should solve it using the original difference equation. Okay. Just again, some recap, reminder. So this is actually that we have so far. So these are the 4 characters that you really need to know to understand. So one is the impulse response. We talk much about impulse response. So we talk much about the difference equation. And last time, of course, this week, this class, we doesn't really talk about a system function because we are focusing on frequency response. Okay, but this is the flow on how you get those system function frequency response. Right, and there's a reason why we do system function, the HZ. Why do we need the HZ? There's a reason for that. And this week, actually, we are focusing on DTFT on how to get a frequency response. And why do we need a frequency response? So because we want to do some analysis. So that's the reason why we do frequency response on input signal, on output signal, on the filter itself. Okay, but up to now, so we don't do that analysis yet. We just do on how to do the transform only. Okay. And yes, of course, again, in test 2, so all of these will be in test 2. So if you do not know what is the impulse response, you'll be in trouble in test 2. If you're not very clear what is the difference equation, you'll be in trouble in test 2. Okay, system function also, the HZ, and of course, this frequency response, DTFT. So where we call it as a H omega, we denote it as a H omega. Okay, so okay, let's look at next example. So find the results of filtering signal Xn with a filter Hn as below. So we have this signal Xn, which is cos 0.1 pi n plus cos 0.7 pi n. Okay, of course, this is just a very simple example of signal. So normally a signal, it doesn't have only 2 frequency. This signal is actually, it's having only 2 frequency. So the first frequency is a 0.1 pi. The second frequency is a 0.7 pi. Okay, so let's, because on normal signal, so let's say you have something like maybe your ECG. Hopefully I'm, okay, just let's say something like this. So this is like a ECG. So what is this? Supposed to be N. This is some amplitude. It can be voltage, maybe. Okay, if the rod of the ECG is actually measuring voltage, so the amplitude will be voltage. So then this is an example of ECG. So maybe this is from 0 up to 10,000 samples. Okay, example. And of course, we can convert this N into T. So if you want to convert it into T, so you need to do this relationship. T is actually equals to N TS. You need to know what is the TS. And normally, any signal, you should be given the frequency sampling. So let's assume Fs equals to 100 Hertz. Then Ts will be 1/100. Okay, then. So what is T? So T is just this one. So you just convert that. T is actually equals to N/100. So at 0, it will be 0 divided by 100. 0 at 10,000. 10,000 divided by 100. So 10,000 divided by 100 is actually equals to 100. So here, so this is actually equivalent to 100 seconds. Okay, so that's how you convert it. How many samples? This is at index 10,000, at index 10,000. So how many seconds? This is 100 seconds. If the frequency sampling is 100 Hertz. Okay, and this signal, so let's go back to our discussion here. So if you look at this signal, Xn, because this is very important so that you understand a signal. This is actually very simple example of signal because it has only two frequencies, 0.1 pi and 0.7 pi. So frequency in small omega. Okay. So we can say that it has the first frequency, omega 1 equals to 0.1 pi. And then frequency number 2 is a 0.7 pi. But actual signal, this one, so how many frequency that you will have? So actually you will have an infinity number of frequency. Okay, you should have an infinity number of frequency. This one, we have only two frequency. So represented by cos 0.pi n, and another one is a cos 0.7 pi n. And actually, what is this? So this is, if you still remember, okay, I bet you don't remember. So this is what we call Fourier series. So this signal is actually in terms of, so we write this, actually this is in terms of a Fourier series. So what is a series? A series is actually a summation of a sequence. Okay, and this is actually, we have a sequence of values, which is represented by the sinusoidal signal. And each sinusoidal signal has a unique frequency. Okay, so that is actually Fourier series. Fourier series is just a series of sinusoidal signal, either cos or sine, with different frequency, with different amplitudes, with different phase. It's a combination of that. And this signal will have a lot of this term, infinity number of this term. If you write it such that, so that will be the Fourier series of this signal. Okay, so that's actually a simple thing. Fourier series is just you decompose this thing into a sinusoidal signal. Okay, so because now we have only a two frequency, so then we can do some analysis, because if we want to do this analysis, so we know that it has a lot of frequencies, but now we can do a simple analysis, because we are targeting on two frequencies only. Okay, and the frequency is in radian. This is what we call an angular frequency for discrete time signal. And of course, you can convert this into frequency in hertz, physical frequency. Frequency in angular frequency in radian per second, you can do that by knowing this Fs. Okay, do you need to memorize the equation? You doesn't need to memorize the equation. The equation will be given in test 2 and exam. You just need to know how to use it, right? So because in this DSP, there's no need to memorize. You need understanding. Okay, so let's see what will be the find the results of filtering signal Xn. So means that what does this mean? So you need to find what is the result of filtering. So this is actually, you need to find the output. Yn. Okay, so what is the relationship? So from the DTFT properties, results of the filtering can be denoted in time domain and frequency domain as below. So where Yn, this is in time domain. So in time domain, it is a convolution. Xn star, so star is not multiply, star is convolution. Okay, convolution between Xn and Hn. Okay, because we can do this. Generally, we can write this a convolution. Either it is a FIR or IIR. But when we want to implement it, we want to compute it. So IIR, we cannot do this. So we can do it only for FIR. So this is our Hn. This is our Hn, and this is our Xn. And our Y omega, if you convert that, transform it. So this is time domain. This is a frequency domain. And of course, straightforward, this is a convolution. Yn of course becomes Y omega. Xn becomes X omega. And Hn becomes H omega. So X omega, this convolution becomes multiply. So where is it? So this is from these properties. Very, very, very important properties. Convolution. Convolution in time domain, it becomes a multiplication in frequency domain. Okay, so let's do that. Okay, so now we know that. So then the magnitude is also when we do this multiply. So we can say that the magnitude of X omega will be multiplied by the magnitude of the H omega. Okay, the magnitude of the input signal and the magnitude of the impulse response should be multiplied in frequency domain. So this one, this is a convolution. Now it becomes multiply. Since the signal Xn has two frequency components, the output signal can be computed by first evaluating H omega at the two frequencies. Okay, so we need to find that. So H omega is actually equals to E minus J 0.5 omega. H E omega. So how do we get this? So let's go back here. So we have a 0.5, 0.5. Okay, I'm going to write that again. Hn is equals to 0.5, 0.5. If you draw, this is 0, 1. Hopefully I can undo that. As 0.5, 0.5. So if we have a 0 here, and we want to find the even signal of this, so this one's supposed to be something like this, where it is delayed by ND equals to 0.5. Okay, then you will get this one. So this is where simply we can say that our H omega is just E to the power of minus J 0.5 omega multiplied by the H of the evenly symmetry signal. So then we will have E to the power of minus J 0.5 omega. So this is a 0.5 times 2 cos. So then you can solve this. You can solve this one using this formula, the symmetry formula. Okay, what is it? X0 plus 2 of the summation, 2 multiplied by the summation of n from 1 up to infinity, the Hn multiplied by cos omega n. So why this is a 0.5? Because the first one here is at n equals to 0.5. Okay, we put it there, 0.5, so multiplied by 2. And then what is the x0? So this is the original x0. What is it? This one. Okay, so then you will get cos 0.5 omega minus j 0.5 omega, and then do that. So you will have this one. This is the magnitude, so which is cos 0.5 omega, because we can just remove this one. We have seen that example. So what is the magnitude? That's h 0.01 pi. So wait, why this is 0.01 pi? Let me look back at it. It's supposed to be 0.1. Okay, something is wrong here. It's supposed to be 0.1, or maybe I'm making a mistake here. Maybe this one's supposed to be 0.01. Okay, so let's see. So what, how the last value will be. So okay, let's assume the first frequency. So which is because we want to evaluate this one at 0.01 pi. So what is actually what we have? What we have? Because we want to know at the output, is this a signal? Because we have two frequency at 0.01. So will it be preserved or will it be removed? Okay, the same thing here. So because this one, we can say that x omega, theoretically, this is a 0 pi omega at 0.01. So let's say this is a 0.01 pi, and this is a 0.7, and this is at 0.7 pi. So it has something. Okay, it has some value here. So we have these two frequencies. So this is xn. If you plot it in the frequency domain, so what should we see? So we should see two peaks. So one at 0.01 pi, another one is at 0.7 pi. Okay, and then at output, so we need to see that will these two frequencies be preserved or will it be removed? Okay, or maybe it will be reduced, or maybe it will be increased. Right? So that's actually a filtering all about. So we need to check this frequency, will it be preserved? So this is where we need to check. We need to check on this frequency. So this is our filter. This is our filter. So what will our filter do at this frequency? At 0.01 pi, so we put in that value. This is omega, replaced by 0.01 pi. So then we get 0.005 because this is 0.5. Okay. So do that. So this is a cos 0.005 pi, and then is this you'll get somewhere equals to 1. So you can try that. Okay, try that, do that, solve that. So I'm writing it here. It is equals to 1. Okay, or maybe close to 1, right? Because maybe this is a very close to 0, 0.005 pi. So this is actually close to 0. And cos 0 is equals to 1. Okay. At 0.7 pi, this is the second frequency of our input signal. So we will do cos 0.35 pi, so which is a 0.45. So then this is the output. So what is the output? Output is just a multiplication of our input signal, the spectrum, multiplied by the spectrum of the our filter. So this is the filter. So this is the filter. So whatever you have in this frequency, you will multiply by 1. And at frequency 0.7, you need to multiply by 0.45. Okay, so okay, let's draw that again. Let's say we have x omega, the magnitude. It must be somewhere at 0.01 pi, and then this is 0.7 pi, and of course somewhere here it is pi. So it has some magnitude. It has some magnitude. So what is the magnitude? In this case, actually, it's not that critical. We just need to say that maybe this is alpha, this is beta. Okay, of course, we need to do some calculation to get what is alpha and beta. So let's assume it is alpha and beta. Okay, and we have our H omega evaluated at 0.001 pi and evaluated at 0.7 pi. The first one, it is equals to 1. The second one, it is equals to 0.45. So now we have x omega and h omega. So what we want to have is actually the y omega. So actually we want to find what is the yn. Okay, so first we need to find out what is the magnitude. Okay, we need to find this thing first. So actually this is just equals to, because of the convolution properties, multiply. Okay, we need to do this. And we have this. So at y 0.001 pi, so this is actually equals to alpha multiplied by 1. Okay, so which is equals to that alpha. So this is actually written here. At y 0.01 pi is actually equals to x at 0.01 pi multiplied by 1. So which is at this frequency, so it is equals to, exactly equals to the input signal, because we multiply by 1. And at 0.7, so this is actually, we look at the frequency of the input signal at 0.7 and then multiply by 0.45, because we have this. This is a 0.45. So we need to multiply these two to get the output. So this is actually at this thing, at this frequency 0.7 pi. So the output is actually 0.45 of the input signal at that frequency. Okay. And actually, we already know that's the magnitude in frequency domain. So it relates to the amplitude in time domain. So now we can say that our yn, so it is actually equals to this thing. The first one doesn't change a bit because this is the same. Okay, this is the same signal. But the second one, so which is should be multiplied by 0.45. So this is actually reduced. So reduced to by 0.45. So instead of the original amplitude is 1. So now the amplitude becomes 0.45. So less than half. So we preserve this one and we reduce this one. So this is actually reduced by, if you can see that, the second term, the amplitude reduced to reduced by, you can see that, reduced by 4.5 is, how many is that? 55%. Okay, so the amplitude has been reduced by 55%. So if you have original signal of the second one, so let's say something like this, so the output will be just half of the, less than half of that. Sorry, this is already misplaced. Let's draw that again. If you have this one as an original, so you will have something less than that. Okay, so this is the output. And this is the input. So it's not a totally removed, but it's a reduced. So it is a reduced. So this signal have been reduced in this case, but not the first one. The first one you still have the same amplitude of it, because we are multiplying it by 1. All right. So if this is a bit complicated, so please watch the recorded video again and try to understand. So what is actually filtering? Because filtering is, in time domain, it is a convolution. So, and a convolution is if you just if you have a simple signal like 2 or 3 samples, and then you can do that convolution by hand. But what is actually the most important thing in a convolution when we do filtering is we want to see which frequency is preserved, which frequency is actually removed, or which frequency is reduced or increased. Okay, this is one example of it, and it is easier to do that in frequency domain, because in frequency domain, the operation is multiplication. Convolution in time domain, it is a multiplication in frequency domain. So that's why we have demonstrate this. So we just do some multiplication, then we can see what will be the output. Okay, so this is actually a filter. Filter is just if you want to preserve frequency, make sure you design a filter on that frequency equals to 1. If you want to remove that frequency, certain frequency, if you want to remove certain frequency, so you just design your filter so that it will be 0. The magnitude will be 0 at that specific frequency, the frequency that you want to, the one that you want to remove. Okay, so that's why this is the same thing. The one that we have a sketch just now. I think we have that. This one. So this is a filter. So what will this filter do? At this point, it will magnify the frequency by 4. But at a frequency pi over 4, because this is a 0, so it will remove that signal. If our input signal has a frequency of a pi over 4, it will totally remove, because it is multiplied by 0. If you multiply by 0, it will gone. Okay, anything multiplied by 0, it will be 0. So means total remove. The same thing here, if you have a frequency of a 3 pi over 4 in your input signal, after you do a filtering with this filter, so it will remove totally that frequency. And you can see that on the rest, this is maybe reduced because 4 is there. So this is somewhere 2. So this is 1. At this frequency, it will be preserved. The rest is actually magnified. So this filter is actually, most of the frequency will be magnified. 2 frequency will be removed. Some of it will be preserved. Okay, because of that operation, multiplication. Okay. So we have go beyond the time. So this is one already. So any questions? Last question. If you have any questions, I'm sure everybody already tired for 2 hours. Okay. So if you have, yes.
I have a question regarding the slide actually. Doctor, I think the slide you upload to e-learning is different from this current one. I don't see the example seems to be different.
Yes, maybe I uploaded a previous version, but I will upload this one also.
Okay, that would be nice. Okay.
So, but of course, I need to wait for we finish this week, and then I will upload it.
Because I need to like annotate on the notes and doing a.
Okay, then I will upload it by today.
That would be great.
Okay, I will upload this new version by today. So please check e-learning later today. All right. Any other questions? Okay, so if you have any questions, actually you can use. Actually, I'm checking your attendance because you put in your what is the most part that you understand, what is the most part that you don't understand. Actually, I'm reading that. Okay, I'm tweaking my my lecture by looking at those things. So if you have any question later, maybe, so you can actually by filling that attendance form, so you can write down your equation. You can write down your questions. Okay, so if you doesn't want to message me to have a question, you can also ask question using that form. Okay, so just please fill in the attendance because that one is quite important for the record. Okay, I think that's all for today. So, Assalamualaikum warahmatullahi wabarakatuh and a good afternoon, everybody. So, see you guys again on Thursday.
Waalaikumsalam. Thank you, Doctor.